Well, thank you very much for the introduction. And it's a very great honor to receive this award, not just because it's an award and we all like to get awards, but in particular from this community, because I think this community is really as strong as any community in the social sciences, or perhaps indeed in any community in the sciences anywhere. And I know that I was chosen out of a field of very worthy other candidates, and I joined a group of folks who have won in the past who've been very worthy. And so indeed it is quite a high honor to have been selected for this. And I certainly appreciate that, and certainly hope that the vote of confidence in my work demonstrated by this will have been justified in the years to come. But we'll see that in the years to come. Today, we're not going to do that. All right, before I begin, I would like to make some comments of some thank yous. There's a huge number of people that I have to thank, and indeed, there's something sort of awkward about getting an individual award when you're a structuralist, okay, because we're all very acutely aware of the fact that nobody accomplishes much by themselves. And if we have success because we're in the right place, we have the right influences and the right sources of support. Okay, and I have a whole lot of them, and I can't possibly thank them all, and not even all of them are up on this slide, but I'll just mention a few people by name, and if I don't name you, and you should be named, then I apologize in advance. But certainly I would like to begin by thanking my partner, Joy Pixley, who has put up with me for many years, and indeed has even collaborated with me on occasion, proving that it can be done. I would like to, of course, thank Kathleen, my graduate mentor, who's gave me a great deal of support through grad school and since. As well as my other mentors and colleagues in the Carnegie Mellon and Pittsburgh community, particularly David Crackart, who is also up there. I'd like to thank my peers at Irvine, especially Katie Faust and Lynn Freeman, who have also been greatly supportive of my work in the last several years. I've had other numerous collaborations. I've been very fortunate to have one. I'll particularly mention the support of Mark Hancock and Martina Morris at the University of Washington. I've had great pleasure of working with them on a number of projects over the years, and they've also been a really great source of support and mentorship to me. Finally, I'd like to extend sort of another special thanks to the folks you see at the bottom who are my students and both advisees and student researchers. One of the fun things about my job has been having the opportunity to work with really bright, motivated young people who are doing great things. And certainly, insofar as I'm able to accomplish something, it's in part because I'm backed up by this great team of great folks. So it's been a real honor to work with all of them so far, and I certainly hope to continue in the years ahead. All right, so given that, let's get down to business. Okay, I'm going to begin with a sort of metaphor, because it's fun to begin talks with metaphors. And the metaphor I'm going to begin this talk with is the funnel, all right? And I don't mean your kitchen implement. Okay, what I mean is the kind of narrowing of possibilities that takes place when we engage in scientific deduction. So we approach a problem for the first time. It may seem as though anything is possible, right? We have this vast set of conceivable possibilities of what might occur, all right? But out of all of those possibilities that we could conceive of, not everything that's conceivable is actually possible, okay? So only a subset of those things are actually possible once we work out the details. And it turns out that, of course, we then think about what is possible. Not everything that's possible is a priori probable because, okay, there are different numbers of ways different things can happen, and once we take into account base rates, we realize that some of these things are a priori much more likely than others. Okay, and then if we look at what's a priori probable, once we take into account the specific details of our context, covariates, and whatever else, okay, we find that not everything that's a priori probable, in fact, is probable in context, and then, of course, out of that, not everything that is probable actually is observed. Okay, so the challenge, in a sense, to the theorist is to find a way to, as quickly as possible, narrow the set of possibilities from that initial broad set of sort of things we might conceive of naively down at the end of the day to what actually happens. And so the goal is to get as narrow as possible, as fast as possible. And what I'm going to talk about today deals with sort of different things we can do at each stage in this process to sort of funnel down our set of possibilities. Now, I specifically titled this talk, The Importance of Simple Things. And in fact, I had considered, for those of you who know the illusion, I had originally considered titling it Chance and Necessity. But so some of you will get that and some won't, and I won't explain it. But maybe if someone asks, I will later. But why I decided instead to go simple things, and the question is why the importance of simple things? And the answer is that when I reflected on my work, what I realized is, I make use of a whole lot of very basic things that are, in fact, quite simple, Some of them, in fact, go back to ideas that have been around for a very, very long time. They're not necessarily even new ideas, but they're often overlooked. And I think that in many cases, attending to these very simple, basic ideas can give us a lot of insight into the social world and why networks are the way they are. I also think that this is really the most effective starting point in most cases for building theory. And in this, I sort of in the Mayhewan tradition, that if you're going to begin building theory of something, you ought to start with saying, well, what are the basic things I know? What are the simplest things I can take into account? And see how far they take us. Now, they may not take us all the way to the end. The world is not always simple, okay? But nevertheless, there's value in seeing how far we can get. So what I want to do today is review some simple ideas that can tell us, I would say, a surprising amount about ostensibly complex networks. All right, so I'm going to begin my discussion at the top of the funnel, and I'm going to work my way down. So at the very beginning, we begin with the idea of fundamental structural constraints, right? So it may seem at first blush, when we first approach networks, or indeed any social system, that anything is possible, right? You hear people talk about this in social science all the time. Oh, the problem with social science, everything is possible, anything can happen. But that's not true. Okay, when you actually sit down and look at the networks that are possible, in fact, networks are highly reductive systems, right? There are only so many ways you can build networks, and there are certain intrinsic constraints and structural properties. You fix one property of a graph, it changes other properties. So in some ways, networks are less like some massive canvas with sort of infinite supply of paint to paint on. They're a lot more like that little infant toy you probably had when you were a child, okay, where you got little pegs and holes, and you put the pegs in the holes. If it's the wrong peg, it won't fit the other hole. And you probably got bored with that and stopped playing with it, because frankly, it's not a great toy. Okay, but it's great from a scientific point of view, all right? Because having few options means that there are only so many ways things can work out, and we could potentially leverage that to learn about the world. All right, so how do we do this in practice? Well, one place I like to start is with a set of relations that I like to call the basic graph theoretic identities. All right, so what's the idea? Well, let's start with a simple graph, all right? And mostly I'm going to talk to you about simple graphs and not digraphs or other such things, although the ideas do generalize. But let's take a graph, which is, of course, a combination of a vertex set V, a set of points that are going to have relations on them, and a set of edges E. All right? And we have some number of vertices, we'll call that N, some number of edges, we'll call that M, and then we can identify things like the density of the network and the mean degree of the network. And there's this cute relationship among these things, which is that if you take those four things at the end, if you give me two of them and pick a third, I can derive the third from the other two. All right? Any two fixes the others. Okay? And in a way, that's very basic, and I'm not going to derive it here, but you get it from simple algebra. It's not very complex. But the implications of this are, in fact, rather non-obvious. And in fact, the recognition that maybe there's something deeper, and this goes back at least to sort of Mayhew and Levenger, who started out asking the question of why is there so much crime in cities, and by taking a relational approach said, well, gee, we should be asking the question, why is there so little crime in the cities? Because once you took into account base rates, okay, things proved to be not like they appeared. But how can we actually use this? So let me take a particular example. So let's say I have a simple graph, and let's consider the mean degree, all right? Mean degree here, just by definition, right? It's the sum of the degrees divided by n, okay, which is equal to twice the number of edges divided by n. And then we can apply the identities and say, oh, I can write that in terms of n and the density, all right? And it winds up being something very simple, right? If the density is the marginal tie probability, it just says, okay, marginal tie probability by the number of people you could be tied to is your expected degree, all right? And if we then just divide through, we wind up with this little expression that says, density is just mean degree divided by n minus 1, all right? Pretty basic sort of thing. But this has an implication, which is maybe not quite so obvious, and that is that if you imagine a network or a system that's growing, right, unless mean degree can continue to grow linearly in n, density's got to fall. It has to, no opportunity otherwise. In particular, if this is constant, then in fact it has to fall as 1 over n, all right? Well, you might say, so what? Who cares? Well, the answer is that linear mean degree increase is a tough thing to do in most networks that we study. Okay? First of all, in most of the networks we study, ties are expensive. They take time, they take energy, they might take money. Okay? You have to sustain them, you have to form them, all that bad kind of stuff. You stop talking to your friends, after a while they drop you, all that kind of thing. Okay, so here's the problem. Given that n can vary by many orders of magnitude in large systems, it's very hard for degree to keep up. To keep adding ties linearly is very challenging. Okay, and if there's a particular maximum degree, that you simply can't sustain beyond that, and if n continues to go up, eventually density's got to fall. Likewise, even if you're keeping up to some extent, you just don't keep up linearly, then in that case, if you're sublinearly adding ties, it's still the case that density has to fall as the graph size grows. And this can lead, if it's misunderstood, to what I will call the sociality paradox. It's not a true paradox, right, but it's an apparent paradox. So let's imagine a system like, say, a friendship group. Okay, let's imagine people keep joining our friendship group. It keeps growing. And let's imagine as people come in, we keep making new friends, right? And so we keep adding ties. But we add ties a little more slowly than people come in. So we add them sublinearly. Okay, in that case, if we observed snapshots of that group over time, or if we had multiple different groups at different sizes, what we'd observe is that individuals in a large group would have more friends in the groups on average, but those groups would be less dense, right? So they're getting more and more and more friends, and the graphs are getting sparser and sparser and sparser and sparser. Okay, so this is the sort of apparent paradox. How is it that things are getting sparser if we're having more friends? And the answer is just what we saw earlier, right? It's not just enough to have more friends. You got to have enough more friends, okay? But a naive observer who sees this and looks at the falling density may be compelled to try to come up with some complicated explanation. When the group gets big, people don't like each other anymore, and they don't make friends, and all this kind of stuff. Okay, it could be true, but it doesn't have to be. We can't explain it just by this very simple phenomenon. All it takes is something that keeps you from adding ties fast enough. And you might think, well, maybe that's very basic, but in fact, I've seen a fair number of talks and reviewed a few papers, and I will not name names, but it's not at all uncommon to see somebody who say they have a bunch of groups, they compare them, and they find, oh my gosh, the bigger groups are more sparse than the small groups, and then complicated stories begin to emerge about what's going on and driving this. Stories might be right, but before we look for a complicated story, maybe we ought to ask, is there something simple going on? Maybe, in fact, what's going on really just has to do with constraints on adding ties. All right, just to convince you this really happens, I'll show you a couple little empirical examples. Okay, these are somewhat arbitrary. You can find your own if you like. But here we have ties from, in the top right panel, emergency radio communications from the World Trade Center. So these are different groups responding to an emergency of the WTC. Down here on the bottom right, we have organizations responding to Hurricane Katrina and collaborating on projects of both of these networks in very complicated, very disrupted settings. Here's another setting that's a little more settled, Ad Health. Okay, these are friendship in schools. And what you see over and over again when you look at cases like this, when you have comparable sorts of networks comparably collected, you tend to find that, yeah, there's variation in mean degree, but it doesn't vary very, very much. Okay, it might vary over a large variation of n by maybe a factor of 2 or 3. Meanwhile, n is changing by 2, 3 orders of magnitude. So what winds up happening? Density falls off, just as you'd expect. Okay, so in fact, density in general is pretty well represented by this 1 over n scaling. Okay, and that means that in principle, right, other things depend on density. We now know that they're going to depend on size. Okay, and we even know some things about how that's going to work. So just knowing this very simple identity gives us immediately some insight into what's going on as soon as we add the sort of observation that in many real-world contexts, perhaps not all, mean degree tends to be relatively constant. It doesn't have to be constant. It just has to be relatively constant compared to n. All right, what else can we do with this stuff? Well, given these identities, one of the things we can do with them is we can use them to make extremal arguments. Extremal arguments do not have to do with jumping out of planes and arguing with people while you do it. Okay, that's extreme, but not extremal. Okay, what extremal arguments involve is making arguments about extreme cases, about bounds, for instance, on phenomena. Figuring out what's the maximum amount of something you can have in a structure, or the minimum amount, and so forth. And there's a lot of potential value in, I would argue, bounding arguments. And actually, if you look at the graph theoretic literature, you see graph theorists use these things all the time. They're sort of bread and butter. And in fact, there's even a field of extremal graph theory. There's nothing but work on these kinds of problems. But I think they're often particularly helpful to us because they can take something that we may work with all the time, a complicated, perhaps structural measure, and they can tell us something about how it's going to behave by finding upper and lower bounds on it. Sometimes they can reveal complex problems of otherwise intractable models, or properties of otherwise intractable models, and so forth. And the nice thing about it is there's a certain sense in which this stuff is sort of fundamentally robust because we're still dealing here with the limits of the possible. We're still dealing with the first part of that funnel. So let me give you an example here, a descriptive example that I've worked with a bit. I'm going to use this degree centralization. I like degree centralization because it's easy. That's my main reason for liking it. Okay, but it has some scientific motivation too. That's always nice. All right. Motivation for studying degree centralization goes back at least to Bavelis in the 1950s, right, who did sort of pioneering experimental work on group performance and was interested in the fact that if you changed communication structures in groups and you gave them different tasks to perform, the groups differed in how well they perform the tasks. Some would be more efficient, some would be faster, some would make fewer errors, and also how much they liked the task. Sometimes they were pretty happy, other times they hated it. Okay, and what they found was that in general, when groups were more centralized, they did things better, and people hated it more. This is life, okay? Unless you were in the middle of the group, people in the center really liked it. That was great. Okay, now that's been complicated by further work. It's not quite that simple. Okay, but the point is that we know that centralization can matter, and the particular kind of centralization we're dealing with here is one where degree is concentrated on a single vertex. So we've got one person who's got a whole lot of edges, and other people have fewer. Okay, and this is a formal measure. It's a standard thing you can find in Wasserman and Faust. Right? Okay, there's the measure. What this is just saying that degree centralization is equal to the sum over all the vertices of the maximum degree minus that vertex's degree. Okay? And it turns out you can work this thing out and reduce it to something that looks like this, where this is the maximum degree. So what this just says is that degree centralization is just the maximum degree minus the mean degree times n. Okay, that's the raw degree centralization. Pretty simple idea. We usually normalize it, okay, and we normalize it by dividing through by the maximum value it can take for a given n. So the maximum value it can take, it takes on the star. The star is as centralized in terms of degree as a graph can get. So we divide through by that, and that gives us our standard normalized measure. All right? And a lot of people think, so therefore, size is gone. We've taken into account size, right? It's all dealt with, okay? But not so fast, right? Size is not that simple, as we're going to see. So one of the things I got interested in this, actually more from looking at the effective density on this measure. And so what I did is I tried to derive some bounds for this thing. And so essentially what I did was I said, well, okay, we can take this expression. We can then substitute using the identities and reframe it in terms of density. And then we can work out, well, what would be the maximal case at a given density for the maximum degree, and what would be the minimal case for that? And you do some algebra, and it looks ugly, but frankly, it isn't really sophisticated. And you get these nice bounds that tell you how big or how small the measure can be. And if you plot them, you start to see things that look like this. Okay, so this is actually about as small as you're going to see. This is a graph of order 3. Okay, and up here we can see here's the upper bound, and it turns out it's also the lower bound. In fact, things can only exist on this line for this particular structure. Superimposed on this, I have in these sort of big circles, they represent the actual distribution over all graphs of that order, so you can see where they are. Okay, the bigger the circle is and the darker it is, the more graphs are there. It's not very interesting when we look at order 3, but we can now watch what happens if we increase the graph order, we change size, and we say, what happens to the set of possible values of centralization? And we see, hopefully, that in fact this thing sort of evolves, and you can see that this triangular structure moves over here to the left, and then there's this funny thing going on down here with this sawtooth pattern that then gradually sort of recedes as we move away. So what exactly is happening here? Well, if we look at a couple of selected stills from that animation, we can get a closer look at what's going on. So what's going on with this sort of movement of the top part of the triangle here to the left is the top of this triangle represents the maximally centralized graph, the star. Okay, but the star can only occur at one density. And that density keeps moving over to the left, right? It's a lower and lower density as n increases. It has to be. It's a very simple thing, right? While what's going on here at the bottom with this sawtooth, this is an expression of the fact that you can't be equal all the time, right? Because ties can't be divided. So you have this problem that let's say you wanted to make the most egalitarian network possible, but you're at a particular density, so you got certain ties to work with. Well, you try to shuffle them around to make everyone equal, and oops, somebody wound up with more ties than somebody else, okay? Sorry, that's how life is. Okay, and so because this is a discrete system and you can't make it perfectly equal, there's a certain amount of inequality that is necessary at any given density. And now in a large network, it's not a big problem, right? This goes away. But in a small network, it actually can be fairly substantial. And in fact, it can be a good chunk of the centralization. So if you change the number of edges in that graph just by a small amount, you're necessarily going to change the centralization score. And we can see that just by looking at these bounds. Another thing that's kind of interesting to see to foreshadow where we're going to go later, we can also look at the plots of where most of the graphs are. So this is saying where are the graphs in the space of all graphs. And we can see that they don't, in fact, occupy much of the space of what's possible. They're actually increasingly concentrated in sort of a funny little area. Okay, so just because something is possible doesn't mean it's particularly likely. But even just with what's possible, we can see that immediately we've eliminated about half the space that you might imagine. So you might think, gee, centralization could go from 0 to 1 at any time. But that's not true. You can't have large centralized structures. It's just not possible, or that are dense, rather. And so, in fact, we're always confined to the sort of lower half of this plot. Now, seeing how this stuff changes with size points out that, network size here seems to be a major issue. And it's not something we can just simply control for by just dividing something out. Because size changes fundamentally the distribution of both the possible and probable structures and their features. So a question we might ask is, if we look across different kinds of contexts we might be interested in, how are network sizes distributed? How are group sizes distributed? And the surprising thing, I think, for many people is that when you look at this for many different kinds of networks, what you discover is that whether or not small is beautiful, small is common. Okay? For many of the kinds of contexts that we think about, face-to-face conversations, households, firms, contexts in which we do work, contexts in which we spend time, contexts in which we interact with people, a lot of these contexts are dominated by very small groups. And we don't tend to notice it because the big groups are very salient to us. Groups like this one, actually, which is quite large, okay? Or the universities that many of us are associated with, or GE, or AT&T, okay? But those are way, way out of the tail, okay? The vast majority of organizations, of households, of other things that exist, these groups are mostly in the small range. And in fact, you can see that these lines here are demarking multiples of 5. So you can actually see here that most firms in the United States here, about 80%, right, are about 10 or less. Okay? They are not very large. So in fact, when you study a whole lot of different kinds of groups, not all, but a whole lot of them, there are a whole lot of little ones all around. And we don't just have to think about sort of formal organizations as well. Even within a larger organization, you're likely to spend a lot of your time working in teams that are smaller. Okay? The dynamics of small groups are really essential. And noting that we're dealing a lot with small groups simply says that this may have some implications for network structure. So the question is, if we know that a lot of groups are small groups, can this tell us something? Okay, and I'd say it can, because there are some intrinsic limits on small groups. In particular, small groups have certain types of enforced simplicities. Okay? And this is just a consequence of this sort of, peg-hole problem. There are only so many ways to build small networks, and size can limit the configurations that are possible. Okay, in much the same way as once we bounded mean degree, right, once we had large graphs, we found that density had to go down. There are some constraints that emerge in small graphs on the fact that there are just only so many parts you can put together. So a lot of things that we think about as important structural configurations, that we write measures to detect, that we write papers about, many of these kinds of things can only exist if a graph is a certain size. But smaller than that, they simply can't happen. Okay, and that's not a new idea. This idea goes way back to Zimmel. This is Zimmel's famous argument about triads, right? Triads are special, he says. Why? Because if you start with a dyad, right, you can't have brokerage. You can't have exclusion, right? If I exclude you, I exclude myself, right? But as soon as you have 3 people, things are different. You can have coalition formation. You can have brokerage. You can have these things. And the character of interaction that can occur is very different. Okay, but things don't just stop at 3, right? If you're interested, for instance, in the existence of what's called weak power in network exchange theory, you have to have 4 people to have weak power. You can't have it unless you have that. How about cycles that aren't cliques? You can't have that till n equals 4. How about Ron Burt's work, right, where you have the ideas of cliques that are brokered by individuals? Well, you can't get brokered cliques that are non-degenerate cliques until n equals 5, and so on and so forth. Okay, and we could continue to create these things. So the point is, there are certain types of properties that can't exist in small graphs. It's not just true of sort of distinct properties like this. It's also true even for things like centrality measures. So for instance, the smallest graph smallest digraph that has distinct rankings for in degree, out degree, and betweenness and closeness is of order 5. You can't have it smaller than that. There was a conversation many years ago, I remember on SOCNet, looking for, if I recall right, the smallest symmetric network that had distinct maximum degree betweenness and closeness scores. If I remember right, the smallest example anyone could find was something like order 11 or so. Okay, so if that's true, right, that means that most organizations, in fact, are too small to have people in those positions. Okay? So again, it's important to keep in mind these constraints. Now, beyond just sort of identifying particularities, can we identify in a more systematic way how size constrains networks? Well, one way to think about it is to think about it in terms of automorphic equivalence. All right? So we know from sort of basic theory of automorphic equivalence, right, 2 individuals are by definition automorphically equivalent. If I can reassign people's roles in the graph, their positions, I can relabel them in a way that exchanges the 2 people but preserves the structure. And it turns out that people who are automorphically equivalent have all structural properties in common, right? That is, all of the unlabeled properties. So all their centrality scores, their membership in groups and so forth are all similar. Okay? And one of the things that turns out to be true of small graphs is they only have so many of these equivalence classes, which are called orbits in graph theory, to go around. Okay? And so this means that if you're in a small graph, there aren't many distinct roles to occupy, and that means people may wind up having to occupy the same type of role structure, and thus having the same structural context. Okay? So there's literally not enough diversity for everyone to have their own position. So how can we see how much this is true? Well, one way to do is to try to measure it, and here I'm going to use something from some old work by Malshevitz. He in particular came up with a measure called orbit information. This is the entropy of the orbit structure. That is, if you consider sort of the distribution of people into these equivalence classes, what's the entropy of that? What's the concentration of that? So this measure is going to be 0 if everybody's identical, everyone's in the same equivalence class, okay? And then it approaches log 2n if everyone is a unique snowflake, and everyone's got their own distinct position. So if we divide the orbit information by log 2n, this gives us a measure of diversity. At 1, everyone is in their own position. At 0, everyone is in the same position. And if we then look across graphs, we could just simply simulate graphs at different ends, and we can see, in general, how does this thing vary as we look across the space of graphs. So what I'm showing here are 95% simulation intervals, and then a sort of median line for small networks. So we're here starting with 2. We go up to about 15. We can see that by the time we're at about 15, there's plenty of diversity to go around. Everybody's got their own position in most graphs, and that's pretty much what we'd expect from theory. But if we look at sort of smaller networks, and in particular if we look at this especially small region down here, where, say, we're below size 7, we find the vast majority of networks in this case have a lot of constriction, right? There are only so many positions to go around, and people are fairly concentrated. Okay, and this is not these are not big graphs, obviously, but they are big enough to include most households. Okay, they are big enough to include a lot of face-to-face groups. So a lot of contexts people interact, they're going to be very constrained by position diversity. We can also get this result, I should note, by looking at sparsity. So another way to have not much stuff to go around is instead of constraining n, we could constrain number of edges. And if there aren't many edges to go around, I can't create much diversity either. And if we then simulate graphs with different mean degree and different n, we can see, and we look at the mean relative orbit information, we get sort of 3 regimes of simplicity. There's, of course, the low size regime we saw earlier. There's some simplicity down here if you have very low density, as we might expect. I should note that there is also this thing here in this leading edge. This is a high density regime, and that's just saying the counterpart. If I have a really, really dense graph, right, then everyone also has to be the same, right? There's no edge, there are no holes to go around. So in either extreme, it's going to be the case that there isn't a whole lot of diversity, but everywhere else, right, there are potentially a lot of positions, at least for most networks. Now that may seem a little esoteric, so let me try to bring it back to something that's a little closer to what a lot of people think about, and that's power and exchange in small groups. So there's been a lot of work on this in recent decades, and I would regard network exchange theory as one of the great success stories of network analysis, and I could say that because I don't really do it myself. But in fact, Freeman, as I recall, in one conference once said that, you know, if he had his way at the Journal of Social Networks and sort of cut off everything that didn't have high explanatory power, the only things left would be network exchange theory and propinquity. Those who do this, you can feel good. You make the cut. You can continue to publish. All right. But what this theory has told us, backed up by lots of lab experiments, is that there are certain types of relationships that intrinsically give certain individuals advantages in particular kinds of exchange relations. Okay? In particular today, I'm going to focus on sort of exclusive exchange. So in some networks, like something like this, you wind up with equal power. One person doesn't have the ability to particularly exploit the other. Other networks create what's called strong power. One individual can extract almost all of the surplus shared between 2 individuals. Others give some advantage, but not total advantage from one to the other, sort of weak power networks. And we might ask the question, if we're dealing with small graphs that are very constrained, does this have implications for the availability of different kinds of roles that might allow you to accrue power in exchange, right? And that's important if you're bargaining in a household or trying to decide where to go for dinner. Okay, a common problem done in small groups. All right, so how do these opportunities vary? Well, if we look again across small graphs and we simulate networks and we try to classify roles, and here I'm using Cook-Yamagishi equilibrium to identify the best offers, and then I'm simply classifying things in sort of standard language. So it's a strong power network in the conventional sense. That is for all transactions. They're entirely sort of one-sided. It's equal power if all the best offers are equal transactions, and weak if it's sort of neither of those two. And then, of course, we can here have a mix of types. You can have parts of the network that are strong power components, and you can have other parts that are weak power or equal power. The bottom line is we see that big chunks of the network actually are quite equal. So in fact, in lots of networks, we find that almost everything is equal. So it's actually quite hard to get much power exercise in these cases. But there are certain areas in the size distribution where there are lots and lots of opportunities for strong power and or weak power. And so some size regimes are going to be much more conducive to it than others. So if you're in particularly small graphs, around, say, size 5, around that size, actually, in here where a lot of households are, you've got a lot more opportunities a priori than you do if you're way out here somewhere where it's much harder to sustain. Now that's looking across, that's just showing that there. This is looking across all graphs. So here, if we look at and break it down by mean degree, we see it's a little more complicated. So here I'm just showing the most common pattern in each of these sets, again, as estimated by simulation. And what we find is that as long as things are very sparse, you can still get non-trivial opportunities for power exercise. But again, once you start to get any significant size and you start to get high degree, that's no longer really possible. People have so many exchange alternatives that it's very hard to get graphs where there is a lot of opportunity for power exercise. So again, we have sort of basic regimes. We have our low size regime, and here our low density regime in both cases where we get significant strong power. So all of these are examples of this sort of first part of the funnel. These are examples of where we use fundamental constraints to say something about a network structure. And indeed, I think that they can tell us quite a lot. But at the same time, we might still ask the question, okay, well, if we exit these sort of small group settings and we consider things more generally, what else can these sort of low-level things tell us? And we know that as we get larger, the combinatorial constraints are not going to be so important. for the most part. So that's not what's going to matter, but what might matter potentially are the base rates. The fact that there are a lot more graphs of certain types than others, okay, and if there are a lot more opportunities to have a graph that has a certain kind of structure than a graph has a different kind of structure, then it's going to take a whole lot of sort of pressured, selection pressure, whatever, to push the graph out of it. And so this is sort of the inspiration behind uniform baseline models. So the idea is, well, what if we fix a few properties of social structure and we treat everything else as relatively uniform, sort of maximum entropy, then what do we find? And these models are used quite a lot, usually as null hypotheses. So we posit them as null hypotheses, we see what goes on, and in fact, we reject them a lot. So we know that, yes, the world is not entirely random. We know the baseline models do not explain everything. But I want to ask a different question. I want to ask the question of not whether it's all low level, but how much low level structure can tell us, ultimately, about social structure. So a simple way to start getting a handle on that would be to, so let's take a bunch of graphs. Let's take a sample here from the UCI-NEC and PIAC collections. And let's just simply look at how well the mean values of different GLIs from different baselines explain the actual data. So we have the observed data, we have the expected values you'd get from the baselines, and we can say how much variance is explained in the real data from what we would get from just using the baseline alone. All right, and these two displays sort of summarize that information. So at the top panel, you have the undirected graphs. The bottom panel, you have the directed graphs. The y-axis here is variance explained. Along the x-axis are different measures, okay, and then the different bars reflect different baselines. So you can see immediately looking at this, especially in the directed graphs, that size alone as a baseline is pretty lousy. It doesn't explain much. Okay? Occasionally it has a success. In general, it doesn't do a lot to differentiate graphs. But once you start taking into account density and reciprocity in the directed case, you start to do a lot better. All right? So we can ultimately recognize sort of several different classes of things. There are some things that are sort of in these first boxes that the baseline explains almost everything. So the differences between these networks can be very effectively captured by just the baseline effects. And so what do we see in this category? Well, we see mostly triad statistics of various kinds. In the directed case, we see crack-art efficiency, mean component size in the undirected case. Okay, and the ability to explain the triad census shouldn't shock us too much if we've been reading, because we should know from Katie Faust's recent work that, in fact, the triad census is very heavily constrained by the dyad census, and a lot of information in it is actually taken up by the dyad census. But then there are things beyond that. So there are things that, well, we don't explain almost all of it, but we explain a lot of it, a big chunk of it. And so we start to get down into things like, in the undirected case, crack-art efficiency, crack-art connectedness down in the directed case, things like eigenvalue ratio, which is a measure of core periphery structure, and so on. So there are things in down here that we can do something with, but we don't explain everything. Then we can keep going down. We get things that we can have a good chunk of, but certainly not everything. So things like transitivity, okay? This is an example of something that pretty consistently we get a big chunk of it, but there's more to transitivity than we can explain with these simple baselines. So there's more going on there than simply that can account for. And then finally, we get stuff here like betweenness centralization that we don't do a good job of at all. Okay, so the baselines are not very good at telling us much about betweenness centralization. That's something which clearly depends on a lot more than just those baseline properties. So the point here is not that the baselines explain everything, because they clearly don't. But you can see that for what are ultimately 2 or 3 numbers, they do tell us an awful lot about a lot of things. So they do actually contain a lot of information about many properties of the graph, not necessarily all information about all properties. So that takes us sort of still further down our funnel. All right? So we've now talked about things that are sort of intrinsic constraints. We've talked about things that are due to sort of base rates. And then the question is, well, what if I were to bring in extra information? If I was going to bring in something from the specific context, how well could I do then? How could this add to my ability to understand the network? And there are a lot of things we could do here. We're talking about bringing in covariates, right? And there are many, many covariates people bring in. And at this conference, you've seen dozens of talks with dozens of different kinds of covariates, right? But what would we want if we were looking for sort of general covariates that would do a good job? Well, we would like to find things that are simple, things that are going to be fairly powerful. We don't want to have like oodles of covariates, each of which explains some tiny fraction of what's going on. We want things that are reasonably well-defined and measurable. We don't want things that we're going to spend half the time arguing over what we mean by that and is it well-defined. And ideally, things that are broadly relevant, things where that same kind of covariate is going to have explanatory power over a wide range of networks, not just something that only works, works beautifully, but it only works for explaining, shared wrist-flicking behavior among people, who are sitting outside in that particular bay this afternoon. Okay, it might be a wonderful covariate for that purpose, but it isn't going to be very helpful in general because we want to deal with new problems, not just the same problem over and over again. So a good example of a covariate that does quite well for this, I would argue, is distance, basically, geography. why distance? Why is this a useful thing to look at? Well, first of all, it's got a very well-documented impact on networks. And this, you can go back all the way to Bussard's study of marriage in the 1930s, okay? You want to know what the ultimate aphrodisiac is? It's proximity, okay? You put people together and things happen. At the very least, if you don't put people together, and this turns out to be the key, so we're going to see this again later. If you don't put people together, things do not happen. That turns out to be real key. Okay, so lots of studies here looking at this in different kinds of ways, right up to the present day. And although there are things that are less geographical than others, it's pretty broadly applicable to a whole lot of human systems and animal systems, non-human animal systems rather, at multiple scales, individuals, organizations, and so forth. Okay. So it turns out to be useful in that way. Another nice thing about working with distances is that there are ways to generalize them. So for instance, propinquity, which we'll talk about in a minute, and homophily are very closely related, and there are sort of nice conceptual devices for unifying them. Miller McPherson, for instance, has done a lot of work on this over the years, as well as are factoring in things like effort and cost distances and all that stuff. And there are geographers like Waldo Tobler who have lots and lots and lots of wonderful work on this kind of thing, although I'm going to ignore that for the time being. All right, so what's the research say? Well, it has a lot of detailed things I won't talk about. But the main stylized fact of all of it is what we could call the ubiquity of propinquity. All right, what's propinquity? It's a wonderful word. It's a very 19th century sort of sounding word. We don't get words like that anymore. They don't make them that way. All right, what's propinquity mean? Propinquity is a phenomenon in which tie probability is positively associated with spatial proximity. Things that are close are more likely to be tied than things that are far apart. All right, that's propinquity. So compare here with homophily. Things that are similar are more likely to be tied than things that are not similar. It's a very well-known phenomenon. All right, I mentioned a number of references. One could go on all day with these different things. What I like about it, though, is that we can say a lot more about it than just, it's there or it's not. Okay, because distance is a quantitative attribute, we can very nicely measure how propinquity varies with distance. And one way to do that is to look at the marginals of distance and tie probability. So what's the tie probability on average for a given distance? Okay, and you can express this in terms of a spatial interaction function, or SIF. And when you do that empirically, you get stuff like these panels here on the right-hand side. These are just sort of illustrative, but from some of my studies, okay, on different data sets. We've got data on social friendship, data on phone calls, data on face-to-face contacts, and you get some differences between these things. But typically, when you fit to real data, you find curves that look sort of like this, right? So usually they're monotonic, and usually you find some sort of decay that goes very sharply with distance, often with a very long tail, okay, because you have some ties at long range. I want to emphasize this effect is a robust effect. This isn't just something that shows up in sort of well-settled networks. It also shows up even in disrupted settings. So for instance, one setting that I and my students have been looking at recently has been Hurricane Katrina. So in the aftermath of Hurricane Katrina, actually even before Hurricane Katrina hit, organizations began to mobilize. They came in from all over the country and ultimately all over the world to try to assist with response and recovery tasks. And they wound up working together, many of them. So here's an example from this network from the first 13 days after storm formation of different organizations collaborating in this response. And we can see all kinds of major players from different places, okay, even Everglades National Park, all kinds of stuff coming in. And one of the questions we had is, in this very turbulent environment, where the network is quite novel, people are coming together to solve new problems, okay, to collaborate on new tasks, and it's a mix of people who don't normally get together, would you see, in even an environment like this, would you still see a distance effect, in particular an effect of pre-existing distances? And the answer is yes. Okay, when we look at this data, what we find, if we look at the headquarter distances before the disaster, and we say, does this predict interaction in the disaster? Well, we do find there's a relationship, okay, and it turns out to be basically a power law with a decay of about 1 over the square root of d. And yes, we tried lots of other types of things for people who are interested in that. Okay. There are a lot of other interesting things about that particular point, which I won't go into, but what I want to emphasize is that it's a fairly orderly sort of process. The decay is actually quite orderly in space, even over a very large area, and even though we're dealing with a very heterogeneous kind of system. So even when you're in a very complex, highly heterogeneous sort of system, things like space often tend to act, and in the case of space, we often find that they tend to act relatively smoothly, at least on average. So it's a good, simple thing to pay attention to. So that raises a question. How much can we learn from propinquity? Let's say an oracle whispered in your ear and told you the true marginal relationship for some huge network you're interested in, all friendships in the United States. All right? And you said, oh, I know this information, but what good is it, right? How much will it tell you, potentially? How much can it account for in the structured network? That's a good question. It's not obvious, I would say. But it turns out you can do some work on this and you can find a nice answer. Okay? And essentially what the answer boils down to is that if the SIF, if the spatial interaction function, if this marginal relationship, has this property that for edges that are from individuals that are further away than some critical radius, that you can bound, you can put an upper bound on the tie probability of some small epsilon, okay, and epsilon is quite small, then you can put a lower bound on how much information distance can give you about the network, okay, which ultimately boils down to the sort of fraction of the entropy that it's explained, boils down to the number, the probability of any two individuals being within the sort of critical radius of each other as epsilon gets really small, okay? If that seems confusing and complicated, the bottom line is that, let's say you have a uniform population in some square area, okay, then as long as the critical radius is not too big, like say 20% relative to that radius, you can explain most of the entropy of the network, okay, just from distance alone. And if we look at our empirically estimated examples for many types of networks we've looked at, once you're talking about regions that are 10 by 10 kilometers, 100 by 100 kilometers, once you're on those kinds of scales, distance is going to account for a whole lot of what's going on. Okay? And there's a sort of nice intuition about why this is happening, okay? And it has to do with the idea if you pull people apart, stuff doesn't happen. Okay? Distant dyads are going to be more likely to be null. Okay, and that means that the edges that are going to be present, we may not know much about them, but they're going to have to be within a special rarefied set of edges that are the potential edges among people who are not distant from each other. Now, I know what some of you are thinking. You're saying, this guy promised us to talk on simple things. This does not look simple. All right, let me try to convince you that it is, or at least somewhat simple. Let's try a picture. Pictures are good. All right, let's imagine I have a bunch of vertices. I've embedded them in a space. I'm going to make it Euclidean space. You can relax that. It doesn't really change anything. All right, here they are. And let's imagine that we don't know much about the relationship between distance and tie probability, other than we know where they are, but we do know this. We know that within each individual, we can identify this critical radius, okay, and outside this critical radius, ties are rare. Okay, so they're going to be less than some epsilon, where epsilon is some very small number. Inside, we don't know. They could be, for all we know, they could be certain, but we're not sure. Okay, what does that mean? Well, if we then take all these individuals, we look at who's inside the, who shares a disk, basically who's inside the critical radius. What we know now is that the edges in this network, almost all of the edge probability, right, is going to be for these things, right? So there are going to be some scattered edges out here, okay, but each of these edges is very improbable. The edges in here are going to be quite probable. And if we look at this in matrix form, it sort of highlights what's going on, right? So we start out, we can have edges all over the place in principle, okay, but once we take distance into account, large swaths of that adjacency matrix are going to be primarily zeros. And yes, there'll be some edges here and there, okay, depends on epsilon, which is why epsilon turns out to matter for some of these things. Okay, but if epsilon is really small, almost all of the potential edges are going to be deep in here. And that means you're really dealing with uncertainty about this many cells, not uncertainty about this many cells. Okay, and it's these particular cells. It's not even just the number of cells. We know which ones they are. Okay, and this is part of why distance explains so much. So distance is powerful primarily because it tells you where the ties aren't. Okay, because it tells you large chunks of the graph, they're going to have very few ties on average. Okay, the density is going to be very, very low, and you know where those regions are. Okay, and that turns out to actually have enough information to give you a lot about the structure of the network. Again, not everything about the network. There's some things about the network this is not going to be very helpful for, and it depends on the scale you're operating. But there is a lot about large-scale structure it can tell you. And just to get a visual sense of sort of how this constrained this can be and how this can sort of work out, I'll show you a sort of cute visualization. So this is a visualization of a network that's generated from this kind of marginal process. This is from a testbed simulation that my students and I worked on. This is I'm going to show you the Phoenix SMSA. It's about 1.3 million people. We use census data to generate positions, and then we're extrapolatively simulating from some pre-existing data about face-to-face contacts. It's not a real network, okay? I want to emphasize this is not actual data, but it does give you an impression of how something sort of realistic is likely to look when you are on this kind of scale. And you can immediately see the impact of distance, assuming that the lighting allows you to see it. We're actually kind of flying through the network, and hopefully as we get closer, you'll be able to see the ties emerge as we start to get near the ground, and you can actually see the sort of clusters of ties rolling by on the geography. And you can immediately perceive how sort of where there are dense clusters of people in space, right, this generates much more local density. The ways in which those clusters are linked to each other have impacts on whether or not those clusters are isolated or connected up to others, and so forth. So there's a whole lot about the heterogeneity of the structure of these large-scale networks that you can potentially capture with distance. Okay, again, maybe not everything you're interested in, and whether this is enough depends on what you want to capture. But nevertheless, it can tell us a great deal. And it's certainly a whole lot of bargain out of what is really, in a lot of ways, a very simple kind of covariate. So I want to now draw out the intuition of this a little bit. So I may hopefully persuade you distance is a powerful covariate, and we might then ask the question, if we know that's a powerful covariate, does it give us any intuition about how other covariates are likely to play out, right? Which things are likely to be predictive or not in large-scale networks? So why is distance such a great thing? One, there's a lot of it, okay? Distance, especially when we're talking about populations, right? There's a lot of distance varies over many orders of magnitude, right? I mean, you have the differences. Even we know that there can be effects of even distance across a room on certain types of behavior. Well, then multiply that by, again, many orders of magnitude when you're talking about distances across a continent. So the enormous range of the variable sort of helps us explain a lot. Another thing that's interesting about distance is that you often get more of it when you're talking about big structures. And the reason is because people and organizations and things, they take up space. I mean, as anyone who's been on an airplane recently knows, right? You know, you pack a bunch of people in, you're sitting there squished in, and you're thinking, man, could they have fewer people in this airplane? I'd like to expand it out. And at a certain point, you have too many people, you've got to expand it. Get a bigger room, get a bigger neighborhood, a bigger development, a bigger city, a bigger country, and so forth, right? Human populations expand, organizations expand. Less true in online networks, but in online networks, although things are a little more complicated, there are some analogies with communication spaces. You know, you can only pack so many people into the same, say, discussion forum before they can't hear each other, so to speak, and they move off in their own way, although it's not directly analogous. So I don't want to go too far with that. Okay, but the bottom line is it's sort of this thing varies quite considerably. We get more of it as network grows, and it has a very reliable effect on the average edge. It tells us pretty reliably where ties aren't. Right? And it affects like the whole adjacency matrix for the most part. As opposed to, we can think about, say, a covariate that only activates in special circumstances. So if I have a covariate that acts only to tell me, say, when I'm going to close a triad, right, there are fewer opportunities for that covariate to have a large impact rather than something that is dealing with an effect on every single edge in the network. Okay? So these are all reasons why distance turns out to be pretty powerful. And then we could think, well, okay, what about other types of possibilities? What are about other things? So we think about, say, homophily or xenophobia effects in general. Right? Our traditional way of thinking about them in terms of race, gender, et cetera, these things can be quite powerful, but some of the kinds of expansive influence in large graphs that we get with distance are not going to happen here, okay? Because usually we have a fixed number of categories. Those categories are sort of bounded, right? We're not increasing the categories usually as we sort of get larger and larger scales, at least not to a certain point. They also sort of can't scale in the same way distance does quantitatively. You know, age can actually scale over at least some reasonable amount, but not as much as distance. People can be, you know, tens of years apart, but it's hard for people to be thousands of years apart and still be alive, at least these days, okay? No matter how old you think your parents are, okay, they're not that old, all right? Or these days, you know, professors like me. So anyway, also it's something that's not as likely to show n sensitivity. So again, if you keep piling up a population, okay, the age range expands a little bit, but it's not expanding like distance tends to expand in practice with large populations. Okay, and then we take finally things like complex interactive effects. Well, just as I was saying a minute ago, right? If you're talking about something that only acts in a very contingent way, our intuition at least is that on average, it's probably not going to explain as much information about the total structure. But that's something which is, I think, not quite as clear, and it would be awfully nice to have some formal results here. So there's some nice, I think, open problems about can you place bounds on the predictive power of things that only act in special circumstances. Okay, so given that intuition, what I now want to do is make a conjecture. So I'm going to stick my neck out a little bit and maybe get it chopped off, although probably not today, maybe later. Okay? And I want to make a conjecture about predictive power in networks. All right, here's my conjecture. If we sort of somewhat arbitrarily order networks, and most human networks, and there are some exceptions to what I think would fit here, into kind of a range from small groups, so 1, say, to 15 people, to sort of medium to large groups, 16 to, say, 1,000 people, that bound is pretty arbitrary, to then sort of population level networks, all the friendships in the United States. Okay? I think at least for many of the kinds of networks that we study, if we ask what are likely to be the factors that at the end of the day turn out to be sort of key drivers of what's going on, where are the most powerful effects likely to be, here are some guesses. Okay? I'm going to guess that when we're talking about small groups, combinatorial constraints we're ultimately going to find are a big chunk of what goes on in these groups, for all the reasons we've talked about. There are just only so many ways to put these little tiny things together. Okay? And this is going to place really substantial constraints on what's possible when you have these little groups. But as the group gets bigger, we've already seen from the simulation work, right, these constraints fall away pretty fast. And once we're in even a reasonably medium-sized group, these combinatorial constraints are not going to hold things down. They're not going to be all that important. What about large groups? If we go way out to the large groups, again, I would argue geography and, in general, restrictions on interaction potential are going to turn out to be really critical. Because, again, as things get really huge, it's very hard not to have them differentiate. It's very hard not to have them embedded in some kind of space where they're spread out, okay, to keep from bumping into each other. And, of course, the keeping from bumping into each other itself puts structure in the network. So when you're dealing with enormously large kinds of networks distributed over large spaces, then this effect starts to become very big, and my guess is that it's going to tend to swamp almost everything else. Now, what happens in the middle? Well, I think in the sort of medium to large range, I mean, certainly we know homophily is very important in a lot of dimensions, and my guess is that demographic homophily in many kinds of networks is going to continue to be very, very powerful, independent of everything else. And I think especially when we're talking about sort of large groups that are not enormously dispersed, those may be the most powerful factors we have. But finally, I think if you ask, where do the vertex idiosyncrasies go? Where do all the little funny things that this person is an active person and this person is a sad person, where does all that kind of stuff go, the covariates that many people like so much? Okay, now I'm obviously pretty biased. I'm saying they only live in this little tiny place over here, okay? But what's the actual argument? My actual argument for why I think those things are most powerful there is this. If you get to really, really tiny groups, there are just only so many ways things can work, and anyone who's trying to manipulate that structure for whatever reason is going to keep running into combinatorial bounds. Okay, if things are really huge, then the ability of some idiosyncrasy of one individual to affect the network is very limited, and in any event, spatial constraints and the like are going to tend to box them in. Okay, but when you're in a group that's not tiny, it's big enough that you have freedom, okay, but not so big that you're just lost in this huge sea of space. That's the area in which I think the individual level factors are going to be most powerful. And it's interesting to note that if you look at a lot of the networks historically we've studied, I'd say most of the networks that we've tended to study have been right in this range. Okay, so this might have something to say about why those particular factors have seemed to be important, or perhaps we select them because this is where they're important or not. Or alternately, maybe the entire thing is entirely wrong, which is always a distinct possibility, but that's the fun of making predictions. You get to be wrong or not. Okay, so this could be prescient, it could be naive, it could just be wrong. I think it will take some decades of research, I'm not being super optimistic in that sense, before we have enough information about what predicts what that we will really know whether that's right or not. But I do think it will be interesting to see. And I do think it's at least a worthwhile endeavor for us to try to make some guesses about where the power is going to be rather than sort of do it in an entirely ad hoc way. Okay. So having stuck my neck out, I'm going to go a little bit further. And you give a talk like this, you can't do it without giving a manifesto. So I want to give a manifesto for simple things. There are a lot of classic ideas here, and the things we've talked about today, a lot of these are, as I say, old ideas. You know, Zimmel, all right, doesn't get a whole lot older than that when you're talking about networks. But there's a lot we don't know about these things, and I think there's a lot that remains to be done. So I have a giant wish list of research tasks, which I will now unburden onto all of you. And hopefully you will now go out and do the research to answer these questions. So what would I like to see? What's on my wish list for research on simple things? One, I would love to have some good theories of group size, okay? Now, if we look in, there are some beginnings of this, right? If you go into literature, in the economic literature on firms, there's some stuff on firm size distributions. If you look at the literature on ethology, there's some stuff on animal groups. If you look in the demographic literature, right, you can find some information on some other family size, some other social aggregates. But we don't have a really good general theory of group size. People have made stabs at it over the years, but it's not a settled thing. Particularly not just distributional theories. Could you, if I gave you covariates about a group, could you actually tell me how big the group is going to be? Can you even do it? I don't know, but I'd sure like to have it, so I'm putting that on the list. Also, while I'm at it, while you're working on group size, can you work on mean degree? I think this is important. Okay, we know mean degree drives a whole lot of stuff. But again, if I give you a network without showing you that network and I tell you about its properties, you know, is there a good theory that's going to actually allow you to tell me what the mean degree of that network is going to be? Nope. Not that I'm aware of. There is important pioneering work that has been done over the years to try to start to get at that question, especially coming out of the egocentric network tradition, looking at personal network size. Okay, people trying to estimate those kinds of things. All right, and there's a lot of folks coming out of Russ Bernard's tradition, and Gene Johnson has worked on that stuff, Chris McCarty, lots of other folks, the late Kilworth worked on those things. Okay, but that's a beginning, but that's not an end. Okay, we don't have a good general theory that says if I know these properties of this network, if I give you a bunch of properties of the network that are external properties, covariates of the group, can you tell me what this is going to be? I'd love to know that, but you know, we don't have it. What else? Well, there's a lot of stuff that we can do that's sort of general that takes advantage of what we've been talking about. Right? We know there are all these wonderful graph identities, and yet we don't use them very often. So I think more systematic use of these things to see how much we can milk out of our existing concepts, I think, would be awfully useful. as would, I think, more sort of fundamental theoretical work on predictive power. Again, trying to say ex ante, not just by looking at it. I mean, looking at the data is one thing, but it's awfully wonderful to be able to say ex ante, look, don't bother working with this variable because there's an intrinsic bound on how much it can ever predict. Okay, or this variable over here, this type of variable would be very potentially powerful, so it's worth looking at. So knowing more about what ought to work and in what kinds of contexts different things will work could save us a lot of time and energy instead of just groping around in the dark. I think we obviously need more quantitative studies of homophily and propinquity and so forth. Okay, we have a lot of studies of it, but a lot of them are not quantitative studies. Okay, so what do we know about homophily, right? It's one of these great things that we supposedly know about. Okay, we know that people who are similar, right, are more likely to be tied to each other if they're similar in the right ways, okay, in the right kinds of networks, and to some amount, all right? So people are homophilous except when they're not, all right? That's not a very charitable way to put it. And if I actually had you fill out a bunch of things, people in the room could probably guess pretty well what the right answer is, but do we have, really, really good theories to tell us about this? I'd say we have some beginnings of them, but I don't think we have good quantitative theories to say exactly how much homophily, when, and so forth. And I think that more work on that certainly would be helpful. Finally, while I have my wish list, I will finish my wish list up here with the grand wish of a decent relational typology. Okay? And a lot of these other problems, to approach those well, I think that's going to be important as well. So when we study networks, we tend to do it in a somewhat ad hoc way. I mean, you get network from a particular data source, you have a particular kind of relationship, and in a way it's kind of idiosyncratic. People have tried over the years to put them in some boxes to establish communication networks or friendship networks, but so far none of these typologies have turned out to be very, very theoretically powerful. I would at least argue, and some people in the room who've worked on them are probably very upset at that and would like to disagree with me, and they're welcome to try to convince me that it works because I'm happy to use it. Okay, but what I really want is something where literally if you tell me the properties of the relation, I can put it in a box, I can tell you the kinds of models that are going to work for that thing, I can tell you what's going to predict it, what's not going to predict it, and so forth. Really quantitative theories that tell me what's going to matter. That's important for measurement models. It's important for predictive models. We need to have this kind of stuff. And right now, it's all kind of ad hoc. All right, so I think we could certainly improve in these areas. So these are all things that I think we can improve on, and things where I think there's great work to be done. And maybe the next Freeman Award winner will be someone who goes and solves some of these problems. So those of you who are looking for work, you got some stuff to do. All right, don't say I didn't give you any assignments for homework. All right, it's best not to go on too long, so I'm going to wrap it up with some concluding aphorisms. Okay, so that if you take nothing else of detail from this talk, you can take away these little happy sayings. First of all, don't forget the simple things in life, like size and mean degree, okay, and reciprocity, all right? These are simple things you can carry with you. And when you approach a new problem, you say, oh, I'm confused. Let me haul out these simple things and ask if they can tell me anything about this. Because often these simple things can tell you a lot about the problem. At least they can give you a foothold that you can use to make more progress. Remember also that small things can be beautiful, or if not, you might as well think they're beautiful because they're awfully common, okay, so get used to them. All right, we have its attraction, especially these days, I would say, there's a sort of attraction of studying big networks, and that's important. And hey, I study big networks too, so I guess I can't denigrate it too much, right? That's important, but we also shouldn't lose sight of the fact that there are many important social contexts which inherently involve small groups. And they're very common, and sometimes they're not very prominent, but they're scattered all over the place, and we need to understand them as well. And we need to understand their properties and be different from large groups, and we need to figure out why, okay? So keeping that in mind may also be useful. So one lesson I wish more people in our banking industry had internalized, and that's that you could do a whole lot with simple accounting principles, okay? So if you go to those, I look at those graph theoretic identities I started with, right? And the fact that we were able to tell you, okay, exactly what the shape of the possible centralization scores are. How did we get that? We did that by recognizing that, well, all the accounts have to balance, right? And so if you don't have enough ties in the network, you can't have somebody who's got a certain number of ties, right? You can't have somebody who has n ties if you only have m minus n ties, okay, or whatever else. All right, so keeping in mind, if you've got a complex problem, sometimes just simply sitting there and saying, is there some conserved quantity that I can add up? You can get a lot of mileage out of it. It isn't glamorous, but an awful lot of great stuff is done that way. And then finally, well, if we want to predict globally and think about sort of big systems, I think it's helpful to think locally. Think about the fact that ties tend to be local, okay? And think about whether or not we can impose some notion of locality onto our data, which will allow us to identify large chunks of the adjacency matrix which are going to be mostly empty. Because doing that allows us to sort of, in a way, sort of a priori block the structure, and that can reveal a whole lot about the structure of the network and constrain the problem quite substantially. So on that note, I will give a final thank you to my many collaborators, mentors, and peers, and of course to all of you, both for your work as a community and for your attention here today. And with that, I will stop. Thank you very much.